You know, I've never actually seen benzene. Well, historically they knew that the formula was C6H6, but they weren't sure of the structure. Was it a straight line, or was it kind of a weird square with a bit coming off it? And then a guy called Kekulé had a dream of a snake that's eating its own tail. But your teacher probably told you the story of him having a dream with monkeys holding onto each other in such a way that they make up a hexagon with single and double bonds. That story's not true. Kekulé made it up later on in a satirical magazine, and people think that these dream stories he had anyway were not true. They were just a way for him to cover up the fact that someone else actually discovered that benzene was indeed a hexagon. He got on a stamp, and annoyingly the stamp has the hydrogens at the wrong angle on the left, and on the right it's just not a hexagon, it's something else. So this is the so-called Kekulé structure, alternating single and double carbon bonds, also called 1,3,5 cyclohexatriene. Why is it called that? Well, between the 1 and the 2 there's a double bond between the carbons, 3 and 4, and 5 and 6. Take the lowest number, gives you 1,3,5. Cyclo means a ring. Hexa, a bloody noisy door, eh? Hexa means 6 carbons. Tri means 3 enes, 3 alkene-like bonds. And those double and single bonds can actually alternate positions in this Kekulé structure. Checking the length of a carbon-carbon single bond compared to a carbon-carbon double, compared to, well, what exactly is it in the benzene molecule? Well, let's look at the data. PM is a picometer, which is times 10 to the minus 12 meters. And you can see that the benzene carbon-carbon bond is intermediate between the single and the double. And the same is true for the strength of the carbon-carbon bond in benzene. It is intermediate. So what sort of bond is it? It's not a single, it's not a double. Well, that's how we draw it, one solid line and a dashed line to show it's approximately 1.5. And we draw a circle to represent that. Now you can knock off a hydrogen and replace it with various other chemicals or even elements, and that's called substitution. The benzene ring likes to undergo substitution. That is swapping a hydrogen for something else. The benzene ring does not like to undergo addition on the ring there. You cannot break that ring very easily and add things into it, perhaps a 7th carbon. So substitution, yes. Addition, no. So the carbon-carbon bonds in benzene are a bit strange. Let's look at this energy diagram of the hydrogenation of cyclohexene turning into cyclohexane. You can see that that releases 120 kilojoules per mole. So adding a hydrogen over that carbon-carbon double bond releases a certain amount of energy. Now, if I have 1,3-cyclohexadiene, that's 2 double bonds between the carbons, and I add hydrogen, that's about double the energy, minus 232 kilojoules per mole released. And if I have 1,3,5-cyclohexatriene, 3 double bonds, that's going to release about 3 times as much energy. But here's the problem. 1,3,5-cyclohexatriene doesn't exist. It's actually these kind of weird 1.5 bonds due to, actually, resonance. So when you try to add hydrogen to benzene, it doesn't release as much energy as you expect, because benzene has this extra stability. The 150 kilojoules per mole between what you expect the energy release is going to be and what actually occurs is called the delocalization energy of benzene. And because benzene's more stable than you expect, hey, look, on the reactant side, it's actually lower than where it should be if it was 3 double bonds instead of these weird 1.5 bonds. It's more stable, so it's less reactive. And it's less reactive, it's harder to break that ring because the ring's given it stability. Some quick terminology. Aromatic molecules don't mean necessarily that they smell nice, it just means that they contain benzene rings. And unsaturated means that there are carbon-carbon double or triple bonds somewhere in the molecule. Notice how the pz orbitals, perpendicular to the plane of the molecule, when they hybridize, they make that classic ring structure. And there's two rings, one above the molecule and one below. And it's these delocalized electrons in the ring that give the ring the extra stability, which make breaking the ring unlikely.